This is a Matlab program in order to implement the forward Euler method in order to solve a particular differential equation. This is the differential equation we are going to consider, where I y prime here is the derivative of y with respect to time. Time is going to be the independent variable here, is this one. So that will be our f function in this case, where these b and c are two parameters inside this differential equation, which we'll have to specify later so that we can apply that in more general ways so that we can change the values of the parameters and solve it and apply and use the same program in order to solve different differential equations and make it more general, for example. And besides that, as we are saying, we need an initial condition. That's the initial condition. The y function at time t0 is equal to 1. So first here in these lines here, we're specifying which are the b and c parameters we do have here. That in this case, we're considering them to be -2 and 1. This dot here is because they are real numbers. And of course, you can change that as you wish, just changing this line. And then in the second lines, we are specifying which are going to be our initial and final times. Of course, the initial time is going to be 0 as settled here in this initial condition. And the final time, in this case, I have write it to be 6. So here again, the initial and final times are going to be two parameters on this program. I'm calling them T I need and T max. And these, the values will, of course, the values of the final time, of course, will depend on our needs or requirements. So what do we want to calculate? Here, in principle, there is no special need, so I'm just settled it to be 6. But of course, you can change it and you can write it and consider it to be 5, for example. So once we have the initial and final times, the next steps will be to consider which are going to be the number of time steps we are going to require. And the number of time steps I'm going to consider again as a parameter is going to be nt, and in this case I've considered to be 3000. That of course you can also change it. And once you have specified which are going to be the number of time steps, you're also specifying which are the time steps we do have. And the time step is going to be your time range, which in this case is the difference between time t max and t I need over the number of time steps, which are nt. So these are the two. And then here, the next step is going to specify which are going to be the initial condition. So specifying the time steps, you're specifying which are your time mesh. So you do have like 3,000 time steps. Therefore, you do have like 3001 times that you are going to that you need to specify the y function for all these times. So our y, we are going to store all the information about the y function and time as a vector. So y and t it's going to be are going to be vectors, and the number of components of these vectors are going to be nt plus 1 in both cases. And the first component of the vector is going to be the initial condition. That's why here we are specifying which are the initial condition both for y and t vectors. And the first component of the vector y is going to be settled here in the initial condition is going to be 1. Here 1 is going to be a real number again. And the first component of the vector t is going to be, as said before, t I need, which in this case is going to be 0. But I prefer to keep that as a parameter, so we are changing here the t I need initially from 1 to, because the initial condition is different for different differential equations, so that you just need to change it initially here, and all the rest will change accordingly if you keep that t I need as a parameter. That's better. That's why it's better to keep as much as parameters as you can, so that you just need to change at the beginning where you are settling your parameters, and you don't need to change all the bulk of their programming later. So once you have the first components of the vector y and t, you need to calculate the rest. And for that, you need a time loop. This is the time loop we do have here. And the time loop is the place where we are going to implement the method, in this case, the forward Euler method. And the time loop, we're going to do time loop with this for here. And for the time loop will run with an index, and index we're going to call it j, and this index will run from 1 to nt, to the number of time steps. Okay, and this loop we are going to define all the components of both vectors y and t. So here, the first line, we're specifying the rest of the components of the vector y following the method, the forward Euler method. So let's remember which was this method. So here we do have that the wave function evaluated at time j plus 1. So we do have like j plus 1 component of the y vector is going to be the wave function evaluated at time j plus dt, which is the time step, times the f function, and that's going to be this, or f function according to the way we're using in order to define our differential equation. In this case, the f function is going to be all we have here. This is the f function evaluated at time j. So here we are defining, once we have the j component of vector y, we are defining here the j plus 1 component of vector y. And here in the second line, we're also defining the j plus 1 component of vector t, just using this definition, which is basically the initial time t I need plus j times dt. So in these two lines here, we are defining all the components of vector, all the vectors y and t. For example, if we are applying for the first one, we are applying for j equal 1 here, we have that y2 will be y1 will be the first one, which was defined before, plus dt, and this is the f function defined as a function of j1 and t1, which all were defined before. And here again, in the second line here, we do have that t2, which is going to be the second component of vector t. It's equal to t init plus 1 times delta t. So again, here we are defining, once we have finished here all the time loop, we have to find all these two vectors, y and t. And then what we can do is, for example, use the information. We can use this because we are just having these two vectors, we already have all the information we can have on the resolution of this differential equation. And one thing we can do, for example, you can plot it and to see how it looks like. Here we are plotting y as a function of t. Here is the x-axis, and this will be like y-axis. And here in this the following lines here, we just define like a title of for the graph. We are labeling also the x and y-axis as t and y as a function of t, respectively. And once we have that, we can see what's going to be the result, what's going to be the plot in this case, just applying this forward Euler method. But of course, not only the plot, you can also have the specific numbers and specific, if you require, for example, what's going to be the wave function at specific time, the final time, you just need to go directly to the last component of the vector y and write it and see, and in order to have it, what's the specific value or the precise value for that component. But in this case, we just need to plot, and you want to see how it looks like. So we're going to do that. We're going to see how it looks, and that's what we're going to do. Here we have, that's in this case, this is the result that we have, as you can see here. Okay, I'm going to make it down. So as you can see here, this initial point is 0.1, and then it's going that's until it reaches the minimum here, and then keeps decreasing. So that's in this case, this is our solution. This is the plot we do have applying the numerical method. Again, as we were saying before, it's important to see how stable is this method. It's important to try for different time steps in order to see that trying for different ones, we can see that the method is stable, we're getting the same results. And once we have checked different things and see that the result is stable, we could see that we can trust more the result that we're getting. So here, basically, what we have done is just apply forward Euler method for a specific differential equation.